So I think we've said enough about simple accumulation and the kind of gradual draining of the reserve army that occurs as a result of that. Now let's finally throw in technological and organizational change that occurs either due to capitalists competing with each other or due to centralization that's going to occur. Right? Or, I'm coming in late to add this, maybe for a more sinister reason. But we're going to set aside that more sinister reason, and we're going to assume for the time being a certain amount of goodwill from the capitalists. Let's assume for now that they are not actively thinking about reinflating the reserve army, that they're just competing with each other as we would expect them to, basically. So now we're going to throw that in. So recall that, either because of capitalist competition or because of a recent wave of centralization, either way, let's assume that we have an individual capitalist firm that's going to reorganize itself and implement technological change or some kind of organizational change which improves the productivity of labor. And we mentioned earlier that the way we framed it earlier was that the capitalist has a choice here. Either they can produce more with the same number of workers, or they can fire some of them. And we also made the extremely important observations that regardless of which of these two choices is picked, the capitalist is guaranteed to earn super profits for a period of time, and also guaranteed to have a permanently higher composition of capital. So their C over V is going to be bigger now forever. Or at least it's permanently bigger until the values of the raw materials and means of production that they use goes down for some reason. So it might go down a little bit at some point in the future, but for the immediate moment, for a good while, it is permanently just bigger. And once this new method becomes generalized across the whole industry, then C over V for that whole industry will be bigger. So that was what we said before, and that was fine for what we were doing with it. But this choice between either producing more with the same number of workers or firing some of them, we need to kind of think about that a little more carefully now. So let's think about it this way. The capitalist has a certain amount of capital that they can put forward. That hasn't changed. They're going to implement something new, and that's going to help them in accumulation, but the same amount of capital is available to put forward now than was before that. And so they're going to reorganize their whole firm in accordance with this new technology, and they're going to be using the same amount of capital. And so since C over V is bigger, what that means is that the same amount of capital is now going to be used to purchase less labor than before. And so after completely reorganizing your firm according to this new method, that same amount of capital is going to go less far towards hiring workers. In other words, you're going to need less workers. For the same turnover of the same capital now, you need more means of production and less workers. And so you're just going to have to let them go. You don't fire them, right? You say you don't need them anymore, where your services are no longer required. And you say, good day, good luck in the future, right? That's what happens. And so workers are going to be let go. The way we posed the choice before, it seemed like maybe workers would be let go, maybe they wouldn't. No, workers are going to be let go if we're assuming that the same amount of capital is being used. So, of course, maybe there is some extra capital available. Maybe they can take that first option. But maybe they're somehow able to, find the capital lying around to purchase the necessary raw materials to keep the number of workers that they have and just kind of expand their operation. Maybe they can do that. Well, are they likely to do that? Well, they're not. They're not going to be as likely to do that as they are to just keep the same amount of capital and fire their workers. And the reason for that is because it's riskier. It's a needless risk. You have a certain expected market for your product, and if you produce too much of that product, you might find some of it not being sold, and to the extent that your product isn't being sold, your capital is not turning over. And so if you're thinking about the possibility of maybe overproducing your product, then you're not going to go for this first option, even if you do have the available extra capital to do it. Now, in reality, of course, there will be overproduction. But the important thing to note here is that if we're assuming that the capitalists are successfully avoiding overproduction and that they are innovating this way, then we have to assume that workers are going to be let go. And so if we're ruling out overproduction, which again, we're going to bring that back into the story at the end. But for now, if we're ruling out overproduction, then we have the consequence that in fits and starts, workers are going to find themselves laid off as these processes continue. And the justification I gave here of letting go of workers, by the way, is assuming benevolence on the part of the capitalists. Like, I am not assuming that they might be implementing this technology with the explicit intent of laying off workers in order to drive up the rate of exploitation and inflate the reserve army. I'm just assuming that they're doing this due to competition. Whether or not the individual capitalist is going to be implementing labor-saving technology in order to lay off workers and drive up the rate of exploitation really depends on how powerful that phenomenon is. You know, if an individual capitalist implementing labor-saving technology can notice like significant changes in the overall rate of exploitation due to their individual action, if technological change turns out to be that powerful, then you might expect the capitalist to do this independently of competition, with the explicit intent of laying off workers and nothing more. And that's really what I'm intending to explore in this video. How powerful is the implementation of labor-saving technology as a method of driving up the rate of exploitation and inflating the reserve army? And how powerful that is really depends on how powerful the counteracting tendencies are. What phenomenon are going on in capitalism that are deflating the reserve army? And how do those compare with the tendency to inflate the reserve army due to technological change? If the latter seems much more powerful than the former, then you might actually expect individual capitalists to be thinking about this. So that's just something I want us to keep in mind. But for now, let's give the capitalists the benefit of the doubt and assume that they're only going to be laying off workers due to the reasons I already gave. And so in fits and starts, as innovation occurs, as centralization occurs, as new technologies are implemented, as things are reorganized, in fits and starts, workers are going to find themselves laid off. And so at this point, we have two opposing dynamics. We have that to the extent that there's simple accumulation going on, the reserve army is going to be steadily draining. And to the extent that we have the other kinds of accumulation going on, innovation and centralization, the reserve army is going to be inflating in fits and starts. So it's going to be draining due to simple accumulation, and it's going to be inflating periodically due to the other ones. So the question we have to ask is which one of these tendencies is going to win out? You know, we have some draining of the reserve army, we have some inflating of the reserve army. Which one of those rates is going to be higher? Because if the draining is happening faster than the inflating, then the reserve army is going to shrink over time. And if the inflating is happening faster than the draining, then the reserve army is going to grow over time. And so we have to figure out which one of those is more likely here. And the way that we're going to go about that is that we're going to construct some models and observe some long-term behavior. I think that there's a bit of a tension within this theory that is revolving around the general law of capital accumulation, whether it's a kind of long-term tendency of like an ideal capitalist system, or whether it's like more of a general principle that always applies to the process of accumulation in general. I think that it's kind of both, but I also think that the latter one of those is more important. And so what I'm going to do is I'm going to present, you know, the long-term tendency stuff, and we're going to assume benevolence on the part of the capitalist, but then we're going to use that to transition into the more general principle, which will be done by evaluating that question we asked at the end of the last video. How powerful is this potential weapon of class struggle that is technological change? So I think the first step to constructing the models that I'm going to construct is to bring in Marx's argument for a falling rate of profit. Now again, the point here is to show how powerful technological change is within the context of the capitalist system. And that point is independent of a falling rate of profit. However, you can bring in the falling rate of profit to really construct kind of a climactic model sort of what Marx is talking about in Capital in general. And so I want to do that simultaneously. And so like what I'm still primarily interested in doing here is providing like kind of an introductory kind of popularization of the overall theory that Marx is presenting in Capital, you know, for people that are reading through to supplement the book. I'm not necessarily trying to get bogged down in any of the modern controversies. So hi there, Text from the future here. I just wanted to warn you that I'm about to get bogged down in the modern controversies for about 10 straight minutes. So if you want to skip ahead of that, there's a piece of text on the slide saying that I'm getting bogged down in the controversies, and you can just skip ahead in the video until that text disappears if you want. However, I should mention that the claim that the composition of capital rises over time is controversial, and even the claim that the rising composition of capital corresponds to a falling rate of profit is also controversial. I think some of these controversies are justified and some of them are not. So the simplest controversy surrounding whether or not the composition of capital is going to be rising is the argument that if the majority of the labor saving is happening in the capital goods department and not the wage goods department, then it could be the case that the value of the capital goods is decreasing fast enough that the composition of capital is kept at the same level that it's at and doesn't actually grow. Regarding the overall composition of capital in general, I should note that the layoffs happen regardless of whether or not the overall composition of capital grows. Because like I said, when the capitalist implements labor-saving technology, they're going to be paying the same amount for raw materials and means of production yesterday as they were today, and today is the day they implement it. So their C over V goes up, and so the layoffs are guaranteed to happen. That has nothing to do with whether or not the overall composition of capital grows. So that's something that I think it's very important to mention before we get into this. One of the things that I would like to do at some point in the future for myself, just for my own research, is to figure out what exactly the labor saving has to be between the capital goods department and the labor goods department in order to ensure a rising composition of capital. I think at the moment that as long as you have kind of more or less equal proportions, equal amounts of labor saving in both departments, that you should get a rising composition of capital. But I haven't been able to confirm that yet. And I might be wrong. That, I think, is the most legitimate controversy. A controversy that I don't think is legitimate is a counterexample that Morishima presents in one of the major books that I've been using as a companion to make these videos. In one of the later chapters of that book, Morishima shows an example of technological changes under which the composition of capital actually increases over time, and nonetheless the rate of profit is also increasing. Now, there's two important kind of things that he doesn't really talk about which make this possible. And both of them I think are problematic. The first thing that I would note about this counterexample is that in this counterexample, technological change explicitly does not have a labor-saving bias. He has basically one means of production commodity and one wage goods, like finished product commodity, and the amount of the means of production that is necessary to make the commodity is falling at the exact same rate that the amount of labor is falling. Living labor added is required to make the commodity. So in other words, all of the inputs to the creation of this commodity are falling at the same rate. And it is explicitly not the case that labor is being targeted above the input, which I think is ridiculous. I think it's ridiculous to assume that capitalism does not have a labor-saving bias in its technological dynamism. And I gave some of my reasons for that in the rate of profit video, and by the end of this video series on the reserve army, I'm going to have given a lot more reasons why. It's because of how powerful it is as a weapon of class struggle, which I'm trying to demonstrate here. So that claim I think is problematic. And then maybe more problematic is the fact that he doesn't even mention that in his counterexample, the rate of exploitation is rising exponentially fast and wages are approaching zero. They're approaching zero in a somewhat benign way because the value of the means of subsistence is approaching zero. But nonetheless, I think it's ridiculous to assume that that can happen without a rising immiseration of the working class. Like, remember that mechanism I described in the last video by which, wages readjust themselves to a fall in the value of the means of subsistence. They don't just magically change. When the value of the subsistence bundle changes, like in terms of like how much time is required to make it, like that doesn't immediately translate to lower wages. That has to happen through a class struggle. The capitalists are going to have a fight with the workers to bring the wages back down to something that is reflective of like the actual value. That doesn't just happen in a way where it's like the workers won't notice a thing. They're going to notice their wages dropping. You can't just have that happening, and he does have that happening. I guess in his model where everything is going great for the capitalists and the technological change is saving the regime, as he says, it's that the workers just don't even notice that their wages are approaching zero because their quality of life stays the same. I think that's insane, and I think it's insane to think that through that class struggle that brings down the wages, there won't be knock-on effects that involve bad time for the workers. In fact, there have to be some serious class struggle conflicts here because the demand for labor stays perpetually positive in his example, meaning that the reserve army will never stop draining, meaning that the workers are constantly gaining bargaining power. So in his example, he has a situation in which the workers are constantly gaining more and more bargaining power, while at the same time their wages are dropping. That's not a tenable situation for very long. And so this example is just kind of nonsense. And it's not nonsense, but it doesn't really show much of anything, especially because we already know that a rising rate of exploitation can offset a falling rate of profit. And even with the rate of exploitation rising exponentially faster than the composition of capital, it's still the case that even though the rate of profit's rising, it's actually not like increasing as in getting bigger. It's like approaching a fixed number asymptotically. It's not like increasing without bound. All you're doing, despite having the rate of exploitation rising exponentially faster than the already exponentially rising composition of capital, you're still only accomplishing the task of like stabilizing the rate of profit. You're not actually increasing it. You're approaching it from like a smaller number, but you're really only staying at a specific number at the end of the day. So to say it's increasing is to, again, leave something out of the discussion. When I really looked at all of this closely, I started to more and more to think to myself, wow, this is actually sort of a really powerful case for a falling rate of profit in response to technological change generally. Because if it's this hard just to prevent it from falling, then there's no way that this is going to be happening in reality. So like, yeah, there are weird counterexamples, and I will admit that seeing this example actually made me aware of a mistake that I made in my rate of profit. I overstated the inability for the rate of exploitation to compensate for a falling rate of profit. It can in some very extreme scenarios like this one. But what we have here is a situation in which we basically have the most extreme possible scenario, and even then the rate of profit is truly struggling to climb up. So now I'm just getting kind of like on a tangent, but I do think that with this example, it kind of rubbed me the wrong way, and you know, it's just another example, example number 600 trillion of a mathematician getting lost in his own abstractions. So I don't know. Like, I have a hard time believing that the rate of exploitation can be exponentially growing while simultaneously the reserve army drains at a constant rate, or at least I think even an increasing rate, and have that not translate to some kind of revolutionary confrontation eventually between the workers and the capitalists. So, I mean, maybe this is a counterexample mathematically to like a general claim, but it's not a counterexample to like Marx's breakdown theory. Like the system being constructed is clearly on its way to breaking down. In fact, like, since the rate of exploitation is like the only major variable in this example that he never mentions in the example, I have a feeling that he was aware of this and didn't want to mention it. And that wouldn't be the first time that he does that kind of a thing in this book, where he just fails to mention something that isn't convenient to the arguments he's making. Also, I'm not claiming that this guy is like a hack or anything. He's been a great help to me understanding this material. It's just, I just kind of wonder what this guy's like actual intentions were when writing this book, because he's clearly not writing this book to be like accessible to anybody that's actually like interested in revolution. This is written for like a very academically trained kind of person. And it clearly has a specific agenda, and I don't know. I wonder what he's actually trying to do with this book. So the reason that I'm saying this is that the models that I'm going to construct in this video explicitly assume that capitalism has a labor-saving bias, and explicitly makes a point to fix the rate of exploitation. The reason that we're doing that is to show that there are phenomena present that are going to push the rate of exploitation up, by pushing the reserve army up. But nonetheless, I think that when you fix the rate of exploitation the way we do, and when you assume that capitalism has a labor-saving bias, then I think at that point that you can associate the composition of capital as a decent measure of labor productivity, and assume that as it goes up, the rate of profit has to also go down. And I'm referring to, and by the way, that's the rate of profit measured in value terms. I'm aware of Okishio's theorem. I'm aware of the Perron-Frobenius theorem, or whatever the hell. I'm only talking about the value rate of profit, Marx's rate of profit. I'm still learning this material as well, so some of what I just said could be wrong, but that was just me hitting on some of the controversies before I get into it. The last thing I would say is that I'm using the falling rate of profit to enforce this argument for a growing reserve army, and to kind of put together all of Marx's arguments into kind of a climactic, fun thing. But I just want to note that again, that the major takeaways from what I'm going to show you here don't necessarily hinge on a falling rate of profit, and nor do they hinge on necessarily a falling rate of profit that is falling due to technological changes. The rate of profit can fall for tons of other reasons besides technological changes, and I think that a lot of those reasons are very valid. And any other like reason for the rate of profit to be falling that's like an exogenous thing, like could easily substitute for a technologically induced falling rate of profit. Like, all you need for this argument this kind of climactic argument is that the rate of profit is falling. You don't necessarily need that it's falling because of technology. It could be falling, if it's falling for any reason, then this argument applies in some way. In fact, there's a few examples that we'll see in this video that you don't even need the rate of profit to be falling at all. So, you don't even necessarily need a falling rate of profit. So, in any case, I just wanted to mention all of those things before continuing. But in any case, let's get started. We're just going to assume all the things that we've set up until now. So we have a technologically induced falling rate of profit. We're going to assume that. And I think you can probably see from looking at these equations very quickly what that's going to do to the demand for labor. If G is just A times the rate of profit and the rate of profit is falling, then it looks a lot like D is also going to fall. But let's try to see that very clearly because it's very important. So just to spell this out very carefully, I just have some things written here that we've already kind of said. So we have that the overall composition of capital for society, K equals C over V, is increasing due to innovation and centralization. We have, from the discussion about the rate of profit, that the rate of profit is subsequently falling as long as E is staying still. So let's just assume that it is for the time being. And we also we observed earlier that as the rate of profit falls, capitalists become disincentivized from reinvesting, and so this A number, the rate of reinvestment of a surplus, is also going to be falling. And so we mentioned, just like before, when we were talking about simple accumulation, we have therefore that the rate of accumulation falls a lot if the rate of profit falls a little. It's always going to be falling at a higher rate. So the difference between what we had before and what we have now is that before we had that the rate of profit was falling because the rate of exploitation was falling. Right, we were talking about the workers demanding more because the reserve army was draining. Now we have that the rate of profit is falling because the composition of capital is increasing. And so since the composition of capital is increasing, we can't just ignore these two terms out here anymore. But what we can is that since K is increasing, we know that K prime is greater than K. Remember, K prime is the new K at like the end of the production period, and K is the old K. This is the old one. And so if K is increasing, then K prime is bigger than K, and so K prime plus 1 down here is bigger than K plus 1 up here. And so this term right here is less than 1. And so I can't say that D is equal to G. That would only be the case if K was equal to K prime. But what I can say is that D plus 1 is less than G plus 1. Right? Because if I know that this number is less than 1, I can just kind of replace the equal sign with a less than sign and just say this is equal to some number less than 1 times this. That's going to be a smaller number. And so D plus 1 is less than G plus 1, i.e. D is less than G. So if the composition of capital is not changing, then D is equal to G. But if the composition of capital is increasing, then D is always less than G. In other words, this equation gives me an upper bound for the demand for labor. And what I'm saying is that the demand for labor is always going to be smaller than the rate of accumulation. But the rate of accumulation is shrinking. G is falling. And it's falling way faster than the rate of profit because this A number here. So let's just kind of see the flow of logic here, which is that K growing means that pi falling means that G falling faster than pi means that D is falling even faster than G. It's going to be even worse, right? So basically what we're saying is that a small fall in the rate of profit induces a large fall in the rate of accumulation, induces an even larger fall in the demand for labor, because the demand for labor not only is bounded by the rate of accumulation, but it's also bounded by this fraction here that's guaranteed to be less than 1 if the composition of capital is increasing. So the biggest drop that you get from all three of these numbers is the demand for labor. The demand for labor collapses in response to this process. It falls very fast. And so the overall demand for labor falls. Now, the overall demand for labor, what's its significance here? The overall demand of labor gives us the speed at which workers are at which the reserve army is draining because of simple accumulation. So what we have basically said is that as these innovations occur, the rate of profit is going to fall, but also the overall demand for labor is going to fall. And the significance of the overall demand for labor falling here is that the overall demand for labor dictates the rate at which the reserve army is going to drain from simple accumulation. So the rate at which the reserve army drains from simple accumulation also falls over time. So we've looked at the first rate. We have that the rate at which the reserve army is going to drain due to simple accumulation is going to drop down over time as the rate of profit falls. And that's a very bad sign on its own. But we still need to be thorough here, and we need to consider the rate now at which the reserve army is going to be inflating due to technological change. So a related question to that is, we have this equation here, and it's pretty cool. It tells us when the demand for labor is falling, and that's great. And we used it to productive ends with what we just did. But when is D negative? This equation doesn't really tell us that. We have from this that D is going to be falling over time, but we don't really have conditions from this equation, just from looking at it, on when this is going to be negative. And that's really the answer we're looking for if we want to figure out if the reserve army is going to grow, right? Because remember, the demand for labor is the proportional change in the size of the workforce. So if D is negative, then that means the workforce is shrinking, and that's really what we're looking to confirm. So a few more steps of algebra give us the answer to this question. So we're kind of gonna so this is going to lead us to kind of like the final equation for D. That's going to be like the real kind of impactful one to look at. And the way we get there is that we just plug in for G a times pi, as we've been doing. But now we're going to use our equation for pi. That is a times e over k plus 1. We're going to plug in our evil equation, and then we're going to simplify using that. And the first step of that simplification is going to, of course, to be to find a common denominator here with this 1. So I'm going to rewrite this 1. I have a denominator here of k plus 1. And I'm going to replace 1 here with k plus 1 over k plus 1. And then I'm going to combine these two numbers together into one fraction. And if you'll notice, when I do that, this k plus 1 is going to cancel with this k plus 1, but let me write it out. So d plus 1 is equal to k plus 1 over the new k plus 1, k prime plus 1, times, if you combine these two fractions together, you get a times e plus k plus 1 divided by k plus 1. So that's what I get when I plug in the evil equation for g, and I replace 1 with a fraction of a common denominator, and I combine the two. And then, as I mentioned, this k plus 1 cancels with this k plus 1. And so I'm going to subtract the 1 over to the other side, and then find a common denominator again. So I have that d is equal to a times e plus k plus 1 divided by k prime plus 1 minus 1. And by 1, I of course mean the common denominator version of 1, which is k prime plus 1 over k prime plus 1. And so when I do that, then I'm subtracting both of these terms. I'm subtracting both the k prime and the 1, and so this 1 is going to cancel with this 1. And then I'm going to have a times e plus k minus k prime divided by k prime plus 1. And then the last step is to look at these two terms here. I'm going to basically rewrite this. So k minus k prime, if I subtract out the minus sign, is equal to negative k prime minus k. And the significance of that is that this k prime minus k, that's the change in k. This is the new k minus the old k, so this is minus the change in k. And so I'm going to replace k minus k prime plus k minus k prime with minus change in k. And so I get this final very striking equation that d is equal to a times e minus the change in the composition of capital divided by k prime, the new composition of capital, plus 1. This is the final form of our equation for the demand for labor, and it's extremely striking. But before I get into the details of why this is so important, I should mention that this simplification really did hinge on the rate of exploitation not changing. If the rate of exploitation is increasing, you get a much more complicated equation for D here when you do this kind of simplification, and we are going to consider that. But for now, we're just going to assume that the rate of exploitation is constant, and then we're going to bring it back in later. We're going to basically assume, if you haven't noticed, we're assuming that a lot of things are constant, and a lot of things are simple. And then after we get the result in like the simplest possible way, we're going to kind of slowly introduce all of these other factors one at a time. And one of those is the rate of exploitation increasing. But it'll be easier to think about that once we know that the reserve army is growing, because at that point we'll know that the rate of exploitation is increasing, and then we can just think about what's going to happen with E changing in that one direction. So what's important about this equation is the question I asked. We can figure out from this when d is negative. It's very clear when d is negative because everything here is positive. We have the k prime plus 1, that's positive. So it cannot contribute, to d being negative. A is positive, and while it's not constant, we are going to assume that it's constant, and that isn't something that we'll really have to change. And the reason we won't really have to think very hard about the a here is simply because a is a proportion. It's less than 1. So if you're really, really worried about it, just make it the biggest possible thing that it can be. Because remember, what we're looking for is the condition for d being negative. And the bigger a is, the harder that is, and the smaller that a is, the easier that is. And so if a is less than 1, then it's going to be easier for d to be negative. So if you're really worried about it, just pretend a is equal to 1, and then it's constant and positive. So, you can just make a the biggest thing it can be, and then forget it, and then basically forget about it. E, as we're assuming, is also positive and constant. And so a times e is positive and constant. And we know that k is growing, so this denominator is getting bigger, so d is getting smaller in that sense, but we already knew that. What we really have that's new is this minus change in k. And so what's interesting about this change in k is that this is basically the slope. This is the slope of the composition of capital. It's not the composition of capital itself, it's how fast the composition of capital is changing. So from that, we can conclude one thing, which is that, so then, because a times e is positive and constant, this is just a single number. If this thing right here is increasing, if this change in the composition of capital is getting bigger, then eventually this is guaranteed to go negative. So then if the change in k is increasing, it eventually exceeds AE. Making D negative. So basically, let me write down this condition, because it really is what's very important about this demand for labor equation. We have that D is less than 0 when the change in K is greater than A times E. Which is I think, hopefully you'll agree, this is a pretty striking and interesting condition, right? The change in the composition of capital exceeding the rate of reinvestment times the rate of exploitation. You can kind of see, when you say those two words together, the rate of exploitation, the rate of reinvestment, you can kind of see how these are both set to boost the demand for labor. And indeed, you just kind of multiply by them, and they are the two things that can prevent the demand for labor from going negative in the face of this changing technology. That's what we're saying here. So what does it mean to say that the change in K is increasing? We have that K is increasing, but does that necessarily imply that the change in K is increasing? And the answer is no. It doesn't necessarily have to imply that at all, right? I mean, basically what we have here is the slope of the composition of capital. And so if the slope can be constant, right? And with K increasing, if it's just like a straight line like this, if this is how K is increasing, then this is going to be a constant number, and it may or may not be bigger than A times E. So to say that this is growing is to say that K is not just increasing, but is accelerating. That's what we have to have. We have to have not just that the composition of capital is growing, but that it is accelerating. Just growing. So basically, what we're saying here is that just growing is good enough to decrease the demand for labor. But in order to have the demand for labor truly go negative and have layoffs happen like each period, despite the simple accumulation, you have to have not just that the composition of capital is growing, but that it is accelerating. So to say that the change in K is increasing is equivalent to saying that K itself is accelerating. With time. But wait, we already have that, right? You might be saying, we already have that. Didn't we show this already, that the composition of capital is accelerating in the rate of profit video? And we did show an acceleration in that video. And let's review that argument. So let's remember that argument. What we basically said was that if a capitalist, implements labor-saving technology, then like per hour of output, they have to be buying more raw materials and means of production to be processed in the same amount of time, because they're making their workers more productive. If their workers are now more productive because you've implemented this labor-saving technology, then you've got to occupy them with more stuff than you used to, because they're going to be able to process more of those means of production into commodities than they used to. And we had actually pinned down kind of the proportions in which this needed to change. We had noted basically that since you have exploitation going on, the amount of means of production that you have to buy in order to keep a worker occupied is always exaggerated because you're always getting more work than you actually paid for. And so we had this basically relationship that basically a change in labor productivity. So if we have an increase in labor productivity, then this basically implies, like, per the little c and the little v, for an individual capitalist, we basically have a decrease in v, and it always comes with that an increase in c, such that the change in C is equal to negative 1 plus the rate of exploitation times the change in V. If you want to see why that is, just go back to the rate of profit video. But because of that, you see that since K is equal to C over V, what this means is that you're always going to get a double increase in K, essentially. If V shrinks at all, then you know, if V shrinks at all due to labor productivity increases, not necessarily other stuff, you can decrease V in other ways, but if you decrease V due to making your workers more productive, then it's always going to be the case that this number goes up as this number goes down. This number going down makes K bigger, right? I mean, like, you know, if V was 1/10 before, then you know, and C was 1, then you would have 10 here. And then if you change that 1/10 to like 1/100th, right? If you just make this denominator smaller, like 10 times smaller, then this becomes 100, right? So if you make the denominator smaller and smaller, you get a bigger and bigger number here. And so that's contributing to K getting bigger. But in addition to that, C is also getting bigger because C gets bigger as V gets smaller. And so since C is getting bigger, that's also going to contribute to K getting bigger. And so I took that to mean that K is extra sensitive, basically, to small changes in labor productivity. And I summarized that by basically saying, you know, in a slight abuse of speech, I basically said in that video, I think that K accelerates with respect to V, because we were thinking about small changes in labor productivity as changes to V, and we're actually going to continue to do that in this video because for reasons that we'll get to. And the reason I did that in that video is because I knew that I would need acceleration for the composition of capital in this video, and so I was doing that to kind of place a seed. And I thought that, you know, that logical evidence would help me make a case for the accelerated composition of capital in this video. So I want to be clear before I say this, that this observation here, that delta C is equal to negative 1 plus C times the change in V, and this is absolutely true, and it's absolutely essential to having a falling rate of profit in response to changes in labor productivity. And it's true that this observation does produce, at least initially, exaggerated increases in the composition of capital due to small changes in V. It is true that K is accelerating with respect to V to some extent, but the problem is that V is approaching 0, and if you're approaching 0, you have to be decelerating, right? If we're thinking about how V is going to be changing with time, and we're going to be modeling changes in labor productivity as changes in V over time, then if I start V out at here and I have it like dropping towards 0, there's only one way to decrease towards 0, and that's to do it slower and slower and slower. And so the only way to approach 0 over time is to be decelerating. And so even though K is extra sensitive to changes in V, it ends up not mattering. And the reason it ends up not mattering is because if you think about, you know, the fact that V is decelerating means that, like, the changes in V, these are getting smaller and smaller. And that means that these changes in C, these extra contributions that are the things that are exaggerating K that led to my conclusion about acceleration, these are also getting smaller and smaller. Oops. And so because these are also getting smaller and smaller, these exaggerated increases in K become less and less exaggerated over time. And so the observation that I made of acceleration is a little more complicated than just being that, you know, being acceleration. It's not exactly acceleration. It's like initially kind of acceleration, but then very quickly it levels off to being basically just the case that k increases exactly as fast as v decreases, regardless of this relationship here. So if you found that confusing, you should, because I was confused by it. This wasted a lot of my time. But in any case, the bottom line is just forget anything that I said about acceleration in the rate of profit video. There is nothing that I said in the rate of profit video that really corresponds to anything you can call acceleration. And so we have no logical evidence for the claim that k is going to accelerate with respect to time in a reasonable capitalist system. But regardless of whether we had evidence or not, the task in front of us would be the same. The task in front of us is to model the changes in labor productivity over time. What we're going to have to do is we're going to have to make a decision on how we think labor productivity changes are going to happen over time in a capitalist society. And so we're going to look at a couple of different models about how of capitalist societies in which labor productivity is increasing in different ways, and we're going to see what happens to the reserve army in those models. So the way I'm going to do that is, we have this societal little c, little v, and little s. So have a c, v, and s where c plus v plus s equals 1. These are the little c, little v, and little s essentially from the previous videos on the volume 2 stuff, on the reproduction schema stuff. Per hour of value, basically. If I hand you an hour of value, you can kind of split that hour of value into like an average amount of constant capital and an average amount of living labor, and then you can split the living labor according to the rate of exploitation. And so you can kind of decompose an hour, a unit hour of value in society into a C and a V and an S component. If you're confused by that, watch the first 30 minutes of the second part of that reproduction schema video. So we're going to have these, and we're going to model the changes to the composition of capital in society by basically having these things changing with time. So in those videos, we had these things constant. These were parameters of the system that you could slide around in that app. Here, we're going to actually have these things changing with time. And that's how we're going to model a changing composition of capital. And obviously, that's going to make the model much, much, much more complicated. But that's where the assumption of everything is fine in the market is going to come in and save us. So I've written some stuff in. So obviously, C, V, and S, the whole point is that these things are going to be changing with time. But what we're really interested in having change with time is the composition of capital. And so the decision that we're going to make in order to model, a couple of decisions that we're going to make in order to model this process, we're going to be seeing changes to the composition of capital as we've been seeing them, basically. That is to say, as changes to V, which induce changes to C, according to this identity, that the change in C is equal to negative 1 plus E times the change in V. And so basically, we're going to define a change in K by virtue of defining a changing V. And then C is going to change according to this. And then a somewhat arbitrary, but also at the same time extremely pivotal assumption is that we're going to view changes to V as being modeled as like proportional changes to V. So it's basically we're gonna be looking at changes like along the lines of like V becomes 1/2 of itself, or V becomes like 0.97 of itself, like 97% of itself. We're gonna be seeing like changes in which V becomes like some percentage of what it was before. And you can model any change in any variable that way. But nonetheless, there's some motivation to why we're doing this. So basically the way in which thinking about technological changes or productivity increases in the way that we're deciding we're going to do it here is we're trying to mimic the thought process of a particular capitalist thinking the following. They're going to be thinking, I'm going to implement some new labor-saving technology, and that labor-saving technology is going to allow me to fire some percentage of my workforce. And so the way that like line of thinking kind of translates to what I'm doing here as a model is to say, if y of t is total value output, as it always is, from society, then basically like big V of t, I'm going to try to make it very big, is equal to little v of t times y of t, right? Because remember, y of t can be split into like a c times y of t, plus a v times y of t. Oops. plus an s times y of t, right? We can always take any amount of value, that is the total and including the total value of output from society, and split it into a c part and a v part and an s part. And so I'm going to basically say that, this is like c of t. This is like the total constant capital in society. And then this right here, this is the total variable capital. This is big V of t. Maybe I should put like something like that to make it bigger. Maybe I'll do that. I'll just say that's big V of t. So big V of t, this is the total variable capital in society. Basically, this is total wages. And so since this is total wages, it's connected to the total number of workers. Because let's say that m sub s is equal to the value of the means of subsistence for a single worker. In that case, what if I take the big V of t, the total wages, and I just divide it by the means of subsistence, then what I get is the total number of workers. And maybe I'll denote that capital N of t. And so, and by the way, these C's and V's and S's are, like I said, they're functions of time now. So V is now like a little V of t. S is like a little S of t. C is like a little c of t. But in any case, what this means is suppose that I have a model where I'm, say, repeatedly taking little v to 0.97 of itself. Well, then in that case, so if little v, becomes 0.97 times little v, then what happens to capital V? Well, capital V becomes, 0.97 v, the new v, times whatever the new y is. Let's assume that y isn't changing now for the time being. So suppose y stays the same. For now, I'm going to bring this up in a minute. But in any case, if y is staying the same, then what this is it's 0.97 times v times y, which is 0.97 of what it was before. In other words, if I bring down little v by 3%, then that's equivalent to bringing big V down by 3%, assuming that the total value output isn't changing. And what that translates to in terms of n, well, n is equal to capital V of t divided by the means of subsistence, and that is going to 0.97 times v divided by the means of subsistence, which is 0.97 times v over the means of subsistence. This might be a little excessive, but I don't care. This is 0.97n. So this is a 3% reduction in the size of the workforce. So this is 3% reduction in workforce. So if the means of subsistence is staying the same, which we'll keep it the same just to kind of make things simpler, then I think you see now why this is a natural way to model the technological change. To basically model technological change as like little changes to V, little proportional changes to V, is essentially the same as saying that we're going to be reducing the size of the workforce by a certain amount by a certain percentage. So if I implement some kind of new labor-saving technology, I'm saying to myself, this will allow me to fire 2% of my workers. That is some percentage of the total workforce, and that's exactly kind of what we're modeling here. But there's a bit of a jump there in the logic. We have an individual capitalist saying that I'm going to reduce, my workforce by a certain percentage. But what we're modeling here is the change in the total workforce, the total societal workforce, all of the workers in all of the firms. And this is really the key observation, because when a single capitalist decides to do this, they are thinking along these lines. I'm going to be able to fire some percentage of my workforce. But then what happens? Then their technological change generalizes. Everybody else has to pick it up too. Everybody else has to copy them. And so, if somebody reduces the amount of workers required to make shoes by a certain amount, then that's eventually going to generalize, and the entire workforce of the shoe industry is going to be cut by that proportional amount. And that if you take all the workers in the shoe industry, that is some total percentage of the total workforce. It's going to be smaller than the percentage cut relative to the shoe industry, but when you cut the entire all of the workers in the shoe industry by 3%, that translates to some percentage of the total workforce. If the shoe industry is 5% of the total workforce, then it's going to be like 0.03 times 0.05. That's the total percentage of the workforce that's cut. But this is the crucial observation, that an individual capitalist can have like a compounding effect on the size of the workforce. When they implement labor-saving technology, they create like drastic changes to the size of the entire societal workforce. That's kind of important to why the results that we're going to get are going to look the way they do. We're going to come back to this, but in any case, we're basically seeing changes to labor productivity as changes that are reflected in reductions in the total size of the total workforce. Now, I mentioned that Y is staying the same here. So why wouldn't Y stay the same? Well, because of simple accumulation. So basically what we're saying is that this is all assuming no simple accumulation. So it's actually going to be bigger because Y will also be getting bigger. From simple accumulation. And you can see how basically we're going to be modeling simple accumulation and technological change at the same time, and we have a bit of a competition going on. If Y is changing, if this Y is becoming something bigger, then V isn't necessarily becoming 0.97 V. It's going to become something else. Maybe it's 1.01 V. Maybe it's 0.99 V. Is V going up or is V going down? Who knows? That's kind of what we're going to try to find out. What's going to happen to the total size of the workforce over time? That's kind of what we're intending to model. So what I'm going to do is I'm going to basically define two models, and I have apps and desmos for both of them. And they basically amount to different ways in which V is changing with time. The first way we're going to do it, I think, is probably the only way that you can do it that is a sane way to do it as the first thing to do, which is that V is basically just going to be reduced to some proportion R of itself, which is the same each period. So basically it's going to be changes just like these, where you have like V becoming half of itself, V becoming 0.97 of itself, but it's just going to be like 0.97 of itself every single period. So in the next period, it's going to be, 0.97, squared times V. And then that's going to be, 0.97 cubed times V. It's just going to keep happening like this. Every single period, we're just going to have technological changes implemented, which can reduce the workforce by another 3%. It'll probably be something way smaller than that too. It'll probably be like 0.999 V. It'll probably be something very small, but like that's how we're going to model it. We're just going to say basically that each period, productivity changes are made with technology, which allows basically the workforce to be shrunk by like some percentage, and that percentage is given by R. Really, 1 minus R is the percentage that you're shrinking it by. You could basically think of R as like, the kind of aggregate of all of the different technological innovations that are done during a particular period by all of the capitalists, kind of like an average, right? Like this capitalist manages to shrink their workforce by 1%. This other capitalist manages to shrink their workforce by like, some other percent. And if you kind of take that weighted average of all of the, the total percent of the workforce shrunk is kind of like an average, and that's R, or 1 minus R. So we're going to say like, let V of 0, I'm going to denote that like V sub I, the initial V. Similarly, Y sub I, C sub I, K sub I are initial other stuff. And so basically what's going to happen is that we're going to have that V of 1 is equal to R times VI, and R is just some number between 0 and 1. So in what I was showing up there, it's 0.97, right? R is 0.97. And then V of 2 is going to be R squared times VI, and then dot, dot, dot. And in general, we have that V as a function of time is going to be R to the T times VI. So this is the definition. Now, if you're really new to stuff like this, then I should mention that this function, R to the T, for r's that are between 0 and 1, r's that are small, like, magnitudinally between 0 and 1, this is exponential decay. This is basically going to 0 exponentially fast. Goes to 0 exponentially. It's basically exponential decay. It's very slow exponential decay. If r is a very, very big number, then it's still going to take a little while. If r is like 0.9999, it's going to take, plenty of periods to go to 0, but this is kind of an exponential decay. So it's interesting because, you're modeling constant technological change, but that constant technological change naturally kind of corresponds to exponential decay in this little v. And that might seem kind of like cheating, right? It's like, okay, well, if I'm starting with exponential decay in v, then of course I'm going to get an accelerating composition of capital. What kind of assumption is that? And I mean, yeah, but it's like we said, like, this is the natural way to model how technological changes by individual capitalists affect society as a whole. This is the kind of effect that an individual capitalist can have on the whole society with their technological changes. Let's say that I reduce the amount of time that it takes to make shoes by 5 minutes. Well, that is going to correspond to some proportional decrease in the workforce of all shoemakers. Once that gets generalized, once the say a shoe had a value of 1 hour and I reduce it to 55 minutes. Once that technological change generalizes, that is going to correspond to a percentage of the workforce that gets laid off. At that point, only 55 out of 60 as a proportion of shoemakers are going to need to still exist if you still need the same number of shoes. Maybe they'll find jobs somewhere else due to capitalists that are expanding their production due to simple accumulation, but that's how these things look. Because things scale up like that, right? If I implement a new technology and that new technology generalizes, then that will correspond to some percentage of the workforce that is laid off. That's probably the most natural way to model this. I'm not really cheating when I do it this way. This is kind of the most natural way to do it. And so, like, I asked the question at the end of the last video, like, how powerful is this potential weapon of class struggle that is labor-saving technology? And it's really with this observation that we're starting to get a sense of the answer to that. And the point at which you go from the question of how powerful is this to the question of maybe this is actually too powerful is the point where you notice that, okay, so this individual capitalist can cut the entire world's workforce by a certain percentage with their individual actions, but that's not the case for the reinvestment. If they decide to reinvest a percentage of their surplus, that percentage of the surplus that they're reinvesting is not any significant percentage of the total surplus value in society. That is not going to create a proportional increase in the size of the workforce to the same extent that their labor-saving technology created a proportional decrease in the size of the workforce. There's a clear discrepancy between those two actions that the capitalist can take in terms of the effect that these actions have on the total size of the workforce. But to put that conversation in our pockets for now and get back to the kind of modeling at hand, it's pretty obvious that the composition of capital is going to accelerate here, but let's write a little bit out anyway. So I have that the composition of capital as a function of time is equal to little c of t divided by little v of t. And so I don't really know what c of t is, I'll just leave it alone. But I can put, r to the t times vi down here. And so, this is going to 0 exponentially fast. And so I have a denominator that's going to 0 exponentially fast. And so k of t is going to go to infinity exponentially fast unless c is decreasing fast enough to compensate. And so, is c decreasing? Well, no. Because v is decreasing, and we know that c is doing the opposite by the way we're modeling technological change. So we know that the change in c of t is equal to negative 1 plus e times the change in v of t. That's how we're deciding to model things. And so if v is decreasing, then this is going to be negative. So v is getting smaller. So, change in v of t is negative. So the change in c of t is negative something times the change in v of t, so it's negative times a negative, so it's positive. Right? It's negative 1 plus e times some negative change in t, and so it's going to be a positive thing. And so the change in c is positive. If c gets smaller, c gets bigger. So c of t is increasing. It's increasing slower and slower because as I take the same percentage of a number over and over again, I'm getting less and less out of that, and so I'm getting less and less out of the increase. But nonetheless, c is increasing, and v is decreasing, just like we've been saying a million times. And so k of t is growing exponentially fast. And in particular, we don't really need that it's going to zero. We don't really need that it's growing exponentially fast. What we really need is that it's accelerating. Exponentially fast means it's definitely accelerating. And so why is that important? Well, we know that the demand for labor D is going to be A times E minus the change in K over K prime plus 1. And so since K is accelerating, delta K is increasing. So it will eventually exceed A times E, at which point D will become negative. And once it goes negative, it doesn't go positive. And so reserve army begins to grow. Never shrinks again. And it only grows from there. Only continues to grow. So we have it. Within this model, within kind of the simplest possible model that you can construct of this kind of a thing, you have it being the case that the demand for labor is guaranteed to eventually go negative, and once it goes negative, it will stay negative. The rate of inflation of the reserve army, the rate at which the reserve army is inflating is guaranteed to eventually get bigger than the rate at which the reserve army is deflating due to simple accumulation, and eventually the demand for labor will just be permanently negative. You will have workers laid off each period, and you'll have a consistently shrinking workforce. Again, the central assumption here is that the rate of exploitation stays constant. We're going to see that an accelerating rate of exploitation is sufficient to prevent this D from going negative. Except, that doesn't really matter because what we're primarily concerned with here is the rate of exploitation anyway. To say that the reserve army is likely to increase when the rate of exploitation is constant means that the rate of exploitation is probably going to go up, and that's really the conclusion to this whole thing. So, if the rate of exploitation goes up on its own, then yeah, that might prevent the demand for labor from going negative, but that doesn't affect the conclusion. The conclusion is that the rate of exploitation goes up. That's what we're trying to conclude. So, it does, that's mostly the reason why I don't really care that much about whether the rate of exploitation right now is changing or not. We'll bring that in a bit. But, it's not much of a consolation prize to say that an accelerating rate of exploitation might be sufficient to prevent the reserve army from growing. Because the whole point of the capitalists wanting to inflate the reserve army is to raise the rate of exploitation. So if it raises on its own, who cares? And I'm not going to do it. I might make a really nerdy follow-up video to this where I do some of the more complicated math here for like the people that are really into it. But I don't want to spend too much time doing math for math's sake. But I will say that using this, equation for the change in C, you can go ahead and find C as a function of time. You can go ahead and see that C of t, you can do that by basically saying C of t is equal to like the initial C plus the sum of the changes, plus all of the changes in C of t. And you can set that up, and you can reduce, you can simplify it, you can get rid of the big sum and create a real kind of formula for C of t, and then you can say that K of t is equal to some actual function that I can write down, and I'm actually going to make a model out of that, and I'm going to show you the model, but I'm not going to go through this process. But basically once you actually write down the explicit equation for k of t, you can plug in k. You can plug that in here, and you can show that in fact can be shown that d approaches r minus 1 in the limit. And the significance of that is, I think, really cool. The significance of that is that r minus 1, what is that? Like let's say that r is equal to 0.97. That means that, what does that mean? That means basically that every production period, I'm implementing new labor-saving technology that allows me to essentially lay off 3% of my workforce. So so basically what we're saying here is that as time goes, as eventually you're going to reach a point where that's basically what you're doing every period. You're basically just going to be laying off 3% of your workforce every period. It's going to be negative 0.3%, right? So r minus 1 is equal to negative 0.03, i.e. negative 3%. So I'm basically going to be firing 3% of my workers every period at that point. And the reason that this makes sense, so why does this make sense? I think making note of this is going to really tie everything together and make people feel good about this stuff. The reason that this makes sense, or maybe seeing the picture will, or maybe both, you know. The reason that this makes sense is because the rate of accumulation, G, is equal to A times pi, which is equal to A times E over K of T plus 1. Nothing here is changing except for K, right? Because we're holding A and E constant for now. So if the rate of accumulation is given by this equation, well, then this is going to go to 0 with time. And as this goes to 0 with time, it's eventually, what does that really mean? What that really means is that eventually there's either no surplus left to reinvest into simple accumulation, there's really nothing coming out, or, you know, people aren't doing the investment, right? Maybe the surplus is coming out and A is 0. And so nobody's going to, you know, of course, A is constant here. So really what's really happening is that eventually technology reaches a point where the rate of profit gets so low that the surplus that you're getting out each period is effectively 0. And so there's nothing to reinvest into simple accumulation. So there's no workers being hired that way. And so there's nothing to offset this technological change anymore. So i.e., eventually, there is no surplus to reinvest into simple accumulation. I.e., no new hires to offset those being laid off. And we kind of could have seen that already, right? If the demand for labor is getting smaller, if the rate at which the reserve army is draining is shrinking, and the rate at which the reserve army is expanding due to technological change is staying the same, which is what we have here, then eventually the thing that's shrinking is going to be smaller than the things that's staying still, right? If I'm staying still and you're moving backwards and you're in front of me, eventually you're going to be behind me, right? That's what we're saying here, basically. Eventually, this was almost to some extent a done deal once we had that the demand for labor was shrinking as the rate of profit fell. But that's what's going on, and that's why this limit makes sense. That eventually, if r is equal to 0.97, then at the end of the day, the system is basically laying off 3% of its workforce each period. Now, I'd like to visualize this. I'd like to make a little, as you know at this point, I like to see pictures of this kind of thing. And there's only one thing that I need to explain in order to show people a pretty cool picture of this stuff, which is we have to think a little harder about how the growth is happening. So let's try to write down an equation for the total value output over time. And at this point, we can bring in the assumption that we made earlier, which is that there's nothing going wrong in the market. Everything that any capitalist would want. So let me actually write this down. So recall that we're assuming that anything a capitalist wants in the market is always magically available, and anything that they want to sell is magically going to get sold. This is one of the main assumptions that we're making, that we're going to eventually remove and think about But for now, we have been assuming this. And so in that case, what's going to happen? Well, capitalists, like you said in the previous video, are going to sort of just kind of probably lazily reinvest in their own industries. And we can assume then that y of t is going to follow those ideal growth paths that we derived in the previous video. Remember those? In other words, y of t plus 1 is basically going to always equal just like 1 plus a times the rate of profit times y of t. If you don't remember these ideal growth paths that I'm talking about, you might want or want a refresher on why this is what you get when you assume this stuff. Then you might want to return to that previous video and rewatch that chapter. I think the chapter was titled "Deriving Ideal Growth Paths." So if you need a refresher on why this is what you get when you assume this, you might want to jump back there for a second. But nonetheless, this is what you get when you do that. In that case, you know, what you would normally have in that video, the technological kind of coefficients weren't changing. And so a times pi weren't changing. And by the way, we know what this is now. We can say we have a name for this thing that we didn't have in the previous video. Remember that this is actually g. This is the rate of accumulation. We have a name for this now. But in any case, what we had there was that, you know, y of t in general is going to be equal to like 1 plus a times pi to the t times y of t. But that only works because pi is not a function of time, because in that video technology wasn't changing and the rate of profit for a particular department was constant. Here it's definitely changing. So really you can't use this anymore. Not valid. This is, you know, this is still valid as long as you remember that pi is a function of t in the sense that g is a function of t. What we have to say now is that basically, like, you know, y of 0, of course that's just yi, but then y of 1, that's going to be 1 plus, you know, g of 0, you know, times y of 0, which is, you know, that's just y of I, and then y of 2, that's going to be like 1 plus g of 1 times y of 1, but I can go ahead and replace y of 1 with, you know, 1 plus g of 0 times y of I. And then it goes on like that. So you can't write to the t anymore because these things are different. The g is shrinking now because the rate of profit is now shrinking. But what you can write is you can use this fancy notation. Most people have probably at some point in their lives seen like summation notations. I guess through me, because I've been using them sometimes. Right? If I say the sum of all the a sub n from n equals like 1 to 5, then that's just shorthand for like a1 plus a2 plus dot 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 all the way plus up to a5. That's just shorthand to write a big sum like this. And the reason it's a capital sigma is because sigma starts with an s, so it's s for sum. And so if you want to do the same kind of shorthand but with a product, then what you do is you write a big pi, because pi starts with a p for product. I equals 0 to, I guess, t minus 1, right? Because we're saying y of 2 is 1 plus g of 1. That's 2 minus 1. Of all of the 1 plus g of i's times y sub I. So this is y of t in general. But it's basically just the mutated form of those ideal growth paths that we found in the previous video. You just can't use to the power of t anymore because this is shrinking. You have to kind of multiply them one at a time and just multiply all of them. And so basically we're going to be following this growth path, and you can see that as we follow this growth path, we are accumulating, we are like reinvesting capital. As we reinvest capital, we're going to be hiring new workers, but the amount of new workers that we're going to be hiring is going to be shrinking. And meanwhile, there's going to be some firing of workers going on each period, and eventually, what we've said here is that the demand for labor is going to go negative, and despite the accumulation continuing on some very meager level, we're going to get layoffs. And we're just going to continue to get layoffs. And so let's go ahead and see that. So I think there's going to be 3 links to 3 different Desmos apps in the video description. The first one should be titled something like Reserve Army Under Constant Dynamism. So go ahead and click that, and let's finally see all this stuff visually. So I'm looking at the Desmos app that's titled, I think, Reserve Army Under Constant Dynamism or something like that. It's the one for constant technological change. I made another one for technological change that is slowing down over time to model what's going to happen as centralization happens and monopoly forms and such. But this is the simpler version, and I think shows the picture that you really need to see to really understand like the reserve army as like a long-term trend. So the most important curve to look at here, is the black curve. This curve, which rises and then falls again, is the size of the working population. So so basically the way this works is very similar to the model that we came up with in the previous video. You've got a fixed rate of reinvestment of 0.5, that's A. You've got a fixed like little VI, that's 0.2 here at the moment. Fixed rate of exploitation of 1, fixed initial value output of 1. And then basically the big difference between this model and the one we made in the last video is that the little v and the little s and the little c are now all functions of time. These are all changing with time, and they're changing with the time in the way we said. We have this kind of parameter r here, which is at each period, the little v is changing to just r to the t times vi. And so that's really the big difference. The s and the c and all the other stuff is changing kind of along with that. And so that's what's going on. R is right now 0.97, like we kind of set it in the whiteboard. K of t, the composition of capital, that's the blue curve here. And as you can see, it is growing exponentially, right? This is what exponential growth looks like. So that's exponential growth, and there's not much more to say about it than that. And then of course we've got y of t, and you can see that it looks very similar to, it's just the product of all of the like simple accumulations up to that point, right? We've got like 1 plus whatever the rate of profit is times a at that moment, just kind of multiplied by the previous stuff. So you're just kind of multiplying each period by, this percentage given by the falling rate of profit, right? And that's the red curve here. So you can see this one's a little more interesting because it starts off looking like that exponential ideal growth that we saw in the previous video, but then it kind of slows down as the rate of profit falls. So the rate of profit is getting smaller and smaller. The rate of because of that, the rate of accumulation is also getting smaller and smaller. And since the rate of profit is falling, you can see that the returns that you get, the increases in y, sort of become more muted over time. They kind of fall off. And so when you throw in a falling rate of profit and subsequently a falling rate of accumulation, you get basically a growth curve for the value output that starts out looking like those ideal growth paths, but then kind of flattens out and kind of loses steam over time. And so what's going on here is that we're kind of accumulating slower and slower. And so that simple accumulation is eventually not going to be able to keep up with the changing technology. And at that point, right, remember this black curve is the total number of workers. At that point, we just hit a point where we're not actually hiring anybody. And then right after that, it starts to be the case that the workforce declines over time. So jumping to that curve next, that's the black one down here. I'll get to these two in a second. You can see that I've defined the number of workers exactly how I did on the whiteboard, which is that I'm taking the little v of t, and I'm just taking that as a proportion of like the total accumulated value at that point, the total value output, which is just taking this and copying and pasting it down here. So it looks really complicated, but it's just a lot of copying and pasting. And then I'm dividing by the value of the means of subsistence, which is constant in this model. And so the means of subsistence, right, you can see it's like 0.055. The idea is that I can just slide this around and make it a small enough number that n will appear like in a nice scaling way with the rest of the graphs, just to make sure that it shows up and looks nice whatever it needs to be. You can make this whatever you want. It doesn't really make a difference because, it's just a single number times the thing, the real thing, which is the total variable capital. But the idea is that, if you have like, if the means of subsistence is say 1/6, to say, 10 minutes, then 1 hour of variable capital would correspond to 6 workers. And so you can see in the beginning, I have like 4 workers. And so that 4 workers kind of tends to increase as the simple accumulation happens, but then it slows down and you can max out at about 15 workers. And then you start to fall. And the reason that you start to fall is because, we should zoom in on the rates at this point, which are these curves down here. And so obviously these rates are proportions. They're usually things between -1 and 1. So we should probably zoom into the y-axis and change the scaling a little bit. So if I change it to like -0.5 to 0.5, we can see these rates much more clearly. And so what we have here are the 3 rates that we've been talking about that are kind of principal interest. We've got the rate of profit, that is the black curve, P of t, right here. And as you can see, it starts out at like 0.25-ish, and then it falls towards 0 as technology does its thing. And then, the hierarchy that we described is here. So under that, we've got the rate of accumulation, G of t, which is this orange curve. And you can see that the orange curve is basically just the black curve. It is the black curve, just times A, right? Times, I've defined it here. I could have defined it the more kind of careful way where I, do it in terms of the value output, but I just lazily did it as like just A times the rate of profit. It would give you the same thing. And so yeah, it's just the rate of profit times, in this case, a half, because A is 1/2 in this model, but you could change it. It's a little laggy because products are kind of hard for Desmos to do. Desmos has a hard time with stuff like this, so this app is a little less responsive than the other one. But in any case, you've got the rate of accumulation. That's basically just the rate of profit times A. And then finally, below that, we've got the demand for labor. This is the green curve here, the real star of the show. And so as we can see, the demand for labor starts out at about 8%. And so what that means, remember, is that the workforce is increasing by about 8% per period in the beginning. But as the returns due to simple accumulation kind of dry up, as the rate of profit falls, as technology kind of continues its march forward, the demand for labor falls over time. We showed that as the composition of capital increases, the demand for labor is going to fall. And then eventually, because the composition of capital is not just increasing but accelerating, we have that eventually it's going to exceed A times E, and then at that point the demand for labor hits 0, and then it goes negative, and then after it goes negative, it just stays negative. And you can see, if I take the scaling out a little bit, it goes negative right at around like period 40, or like really period like 38. And so if I zoom out again to like minus 10 to like 100, maybe 50 I should say, you can see that that's exactly where the curve like completely stops growing and then changes from growing to shrinking, right around period 38. I max out, and then after that it's all downhill, because the demand for labor at that point is negative. You can see that it goes negative at that point, and then it's just negative after that, and it continues to be negative forever. But you can see that it doesn't just kind of go, the demand for labor doesn't just fall like without a floor. It's falling and it's falling and it's falling. You can see that it's getting closer and closer to a specific number. And that specific number that it's getting closer to, it's getting from like, 0.24, 0.024, 0.025, 0.026. It's sailing, it's headed towards 0.03. And the reason why the reason why it's headed to 0.03 is that 0.03, or negative 0.03 I should say, is r minus 1. Right? I said in the whiteboard that the demand for labor kind of approaches negative 3%, because this is 0.97%. And the reason for that is that as the surplus values that you're getting back each day kind of dry up as the rate of profit falls, you have less and less to reinvest into simple accumulation, and so you're hiring less and less workers that way, and so it eventually gets to the point where that becomes negligible, and all that's happening is this technological change, and this technological change corresponds to laying off 3% of the workforce each period. So it's going to so the steady state of this system really is approaching a situation in which no workers are hired at all each period, and 3% of the workers are laid off each period. That's kind of what we're approaching in the limit. And so, eventually we have a situation in which just 3% of the workforce is being laid off each period. And you can really see in this picture the kind of climactic death of capitalism that Marx is talking about in Volume 1. Because, what's happening here? The number of workers, it's approaching more and more a situation where you have a fully automated economy. Nobody has work, nobody has food, the rate of profit is hitting 0, the capitalists have no idea how to profit anymore, everything is in disarray. You can really see, like, when you put it all together, you can really see, like, the death of capitalism kind of in these curves. Not like the death of capitalism as it will occur in reality, but the death of capitalism in, like, this theoretical model. It's kind of striking how kind of obvious it is, right? But that's the model, and so I think probably seeing a picture like this helps. And you can feel free to mess around with it however you want. And so I hope this app helps people get a better picture, literally, of what the argument for the growing reserve army, in Volume 1 of Capital really looks like. And it certainly helped me to make this. So I hope it helped you too. You can feel free to mess around with it however you want, and feel free to add to it whatever you want. I've got my own kind of alternative that I'm going to get to in just a moment. Maybe one more thing that I just remembered that I can demonstrate within this app. If I zoom in on the rates again, go to like negative 0.5 to 0.5 again, we said a few things about this. One, we said that, so again, just to kind of turn back to that hierarchy for a second, I keep saying that when the rate of profit falls a little bit, then the rate of accumulation falls a lot, and then the demand for labor falls even more than that. And you can see that that hierarchy is very much present here. And I sort of said that already, but I wanted to add one more thing to it, where I meant, we mentioned that if the composition of capital isn't changing at all, then accumulation of capital is increasing the proletariat, in the sense that it should be that the D equals G. And we can witness that in this app. And the way to do that is to go to this R number here, and to say that there's no technological change is to say that R equals 1, right? We're just, V isn't, if R equals 1, then V isn't changing at all between periods. There's no change at all. So it should be the case that as I bring this thing closer to 1, that the demand for labor turns into the rate of accumulation. And you can see that's exactly what happens. When R equals 1, there is no difference at all between the demand for labor and the rate of accumulation. They are the same curve if K is not changing. And you can see also in that case that the rate of profit is also not changing. It's just a constant 1/4. And then a couple of other interesting things to note about this case is that if I zoom back out to -10 to like 50, you can see that first of all, obviously the composition of capital is not changing, but then also the thing I would point out is that this Y curve here becomes exactly the ideal growth paths from that previous video where we derived them. There's no leveling off. It's just pure exponential ideal growth. It just turns into those curves from that video. And then also, of course, the workforce also just kind of grows without bound forever. So that's the case when R equals 1. And you can see basically everything works out how we theoretically assumed it would. But to zoom back in on the rates for one last time, there's a few other things we can still make note of. One is that 0.97 is a particular rate of technological change, but if I lower 0.97 down, then I'm getting faster and faster and more dramatic technological change. And you can see that as I do that, the rate of profit falls faster, the rate of accumulation kind of mimics that, and then the demand for labor falls way more dramatically than both, right? You can see actually what I was mentioning, right? The rate of profit falls a little, the demand for labor falls a lot. You can see kind of that happening within this model, right? The demand for labor is running faster than the other two. And if I even bring it down to like 0.92 or 0.91, like the demand for labor just starts negative. It just starts outpacing the simple accumulation, and there's nothing that the simple accumulation can do at that point to like, the workforce will just be declining from the word go. Right? You can just kind of see it just falls at that point. So that's kind of cool. And so what we've seen kind of is the reserve army argument kind of put into kind of rigorous math and expressed in kind of its simplest form. And the thing that really makes it simple is the way that we modeled technological change over time. We were saying that V of I just starts as something and then basically decreases with basically to a constant proportion of itself each period, right? We just have this R that we're multiplying by it repeatedly. And so the assumption there about technology is that you're getting constant returns from your technological innovation over time. And there's really two conditions implicit to that, right? One of those conditions is constant returns from science, right? That you're not getting diminishing returns from science. You're not reaching a point where like you've just done everything that you can do with modern science, and so you're just not getting as much back over time from science, right? We're assuming that there's nothing like that happening. And I do think that that's kind of accurate in our reality. I don't think that we've reached a point yet where diminishing returns due to science is going to produce a significant amount of declining dynamism. If the will to technologically innovate is there, then I think science is still at a point where it can easily facilitate that. So I don't think that's really a concern. However, there's another reason why R could be declining over time. Another reason that you might get declining dynamism over time is centralization, which we've said is practically inevitable at this point under capitalism. One of the things that I'm intending to suggest with these videos as I make them is that competition is actually not as essential to capitalism's dynamism as a lot of Marxists think it is. But nonetheless, there's kind of a tension within Marxist theory that as monopoly forms, as centralization occurs, and you get you kind of move towards monopoly or at the very least oligopoly, then competition is either going to die down or it's going to, at the very least, the nature of competition is going to change. Right? I mean, if I own my entire industry, if I'm the only one producing my commodity because I bought out everybody else, then there's not exactly much incentive for me to innovate. Now, is there? At least if you're assuming good faith in the capitalist in the sense that they aren't explicitly trying to eviscerate the working class, which is the big assumption that I take issue with. So it's at the very least legitimate to claim that you might get a declining technological dynamism over time within Marx's own theory due to the overall centralization of capital that's occurring. And so I wanted to investigate, how fast does the dynamism need to be kind of falling off in order to not get a growing reserve army? And the answer is interesting. There's some interesting answers to discover here, and I think that when you observe them, you realize that this overall theory is actually a lot more firm on its feet than you might initially think. It's actually not going to completely kill the theory to have declining dynamism over time. So let's jump back to the whiteboard and talk about that just a little bit. I promise we're almost done with the whiteboard. So first of all, we mentioned that when r equals 1, there's no technological change at all. And so what we kind of want to model is we want to alter our model to kind of make r start at something and then approach 1 over time. So we want a pattern like this, basically, where you start at some VI, and then let's say initially technological change is pretty fast. You get like 5% per period. And so we're basically taking that and multiplying it by 0.95. But then it slows down a little bit, and then we're multiplying by like 0.97, something a little bigger, and then maybe 0.98, and then maybe 0.99, and then like 0.995, and then, something, just some pattern of R's that are approaching 1 is kind of what we want. And there's a lot of ways that you can model that. The main kind of functions that model things like this are known as sigmoid functions, if you're a nerd and you're looking for something to Wikipedia. But the example I'm going to use for my model is like consider, let's start with the following sequence. R of t is equal to 1 minus 1 over t. You can see the idea here. Basically, as t gets bigger, this fraction is going to 0, and so I'm subtracting off something that goes closer and closer to 0, and so I'm getting something that's getting closer and closer to 1, which is exactly what I said I wanted here. And so if I kind of used this function and just kind of multiplied by it repeatedly, then it would be like multiplying by an r that's getting kind of bigger and bigger over time. Now, there's a few problems with this, which is, one is that if I plug in 0, I get 1 over 0, so that's let's just put a plus 1 here to make sure that doesn't happen. Now I can plug in a 0. When I plug in a 0, I get 1 minus 1 over 0 plus 1, so 1 minus 1, which is 0. Actually, let me just kind of write this pattern out so we can see what this is. When I plug in t equals 0, I get 1 minus 1, which is 0. And then if I plug in t equals 1, then I get 1 minus 1 half, which is 1 half. And then I get 1 minus 1/3, which is 2/3. And then I get 1 minus 1/4, which is 3/4. And then I get 1 minus 1/5, which is 5/4, or 4/5. I can't do math. And then so forth, right? We get something that's, and you can see, these numbers are approaching 1. And in fact, if I don't want to start at technological change, which completely automates society immediately, which is kind of what I'm saying when I start r out at 0, then I can just add a bigger number here in order to start at something bigger. Like if I put 1 over t plus like 20 here, then I would start at like 1 minus 1 over 21, which would be, something pretty close to 1 from the get-go. And so I can put a number here and kind of tune it so that r starts at whatever I want it to. So I can do that. I can change this to whatever I want in order to make r start at whatever I want. But I'll just leave it at 1 as I kind of go through this theory a little bit. There's one other alteration that I want to do to this r, which is that, I have this sequence that it's going to 1, and it's going to 1 at some speed, right? So this, when I model r by making this r, then I get, a specific speed of technological change. If I did r of t is equal to 1 minus 1 over t plus 1 squared, well, then this is going to go to 0 much faster, right? And so this is a function for r. This is a way to model r in which the technological dynamism is way more dramatic in its decline than it is over here. Here, we get basically science falling off almost immediately, or monopoly forming almost immediately. You get much faster decline with this function than you get with this function. So this goes to 1 much faster. Meanwhile, we could also consider r of t equals 1 minus 1 over the square root of t plus 1. And so this, now I'm basically taking this to the half power, because the square root of t plus 1 is t plus 1 to the 1/2. And so this goes to 1. It still goes to 1, but it goes to 1 much slower. And so by basically tuning this power to be whatever I want, I can make r go to 1 as slow or fast as I want. So in general, the function that I'm going to use to model a declining dynamism is r of t equals 1 minus 1 over t plus 1 to the pth power for 0 less than p less than anything. But I don't want p to ever be 0 because that would just be stupid. And so yeah, you could do it in other ways. There's other ways to model. There's other functions that are approaching 1. You could do some fancy stuff with arctangent or e or whatever you want. But this is a nice way to model it because it's a whole family of different kind of declining functions that are very easy to kind of tune. And on that note of tuning, let's go ahead and change this 1 into whatever it needs to be to generally start r at something that's reasonable. So initially we had, in the previous model, we basically were fixing r as like 0.97. Let's go ahead and make it so that this always starts out as 0.95, just for simplicity. Let's change 1 so that r of 0 is always 0.95. Let's go ahead and do that. So in order to do that, we got to plug in 0 for t, and then plug 0.95 in on the right, and then go ahead and... So if r of 0 is 0.95, then that's the same thing as saying 1 minus 1 over 0 plus x. I don't know what x is. That's the thing I'm trying to find. To the pth power is equal to 0.95. And so if I subtract the 1 over, then I get negative 0.05, but then once I multiply both sides by negative 1, then I get positive 0.05. So after doing both of those things, I have 1 over x to the p, just getting rid of the 0 here and just writing x because that's what I have there, is equal to 0.05. And then if I invert both sides, I get that x to the p is equal to 1 over 0.05, which is actually 20. So I get 20 over here. And then if I take both sides to the 1 over p, if I take the pth root of both sides, then I get that x is equal to 20 to the 1 over p. And so by plugging this in instead of 1, I'm always going to get an r that starts at 0.95 and then gradually approaches 1. So r of t equals 1 minus 1 over t plus 20 to the 1 over pth power to the p. This is a function that starts at 0.95 and approaches 1 at a variable speed depending on p. So if p is smaller, then this is going to go to 1 at a slower pace, and if p is bigger, then this is going to go to 1 at a faster pace. And so this is what I can use as a model. In fact, I could replace this 20 with whatever it needs to be to start r at whatever I feel like. So I kind of have a cool little variable way to model declining technological change. And so basically where I had that v of t was basically like r to the t times vi before, that was really the case because I was really saying that v of like t plus 1 in general was just r times v of t. Now what I have is that v of t plus 1, what I want to say is that this is r of t times v of t. But I sort of have the same issue as before when I was dealing with the ideal growth paths, which is that this is now changing, so I can't just take it to the tth power. What I have to write instead is that v of t is equal to the product j equals 0 to t of r of j, and then that's going to give me all of the kind of multiples, and then I just multiply that by vi. And so this is basically a revised model for a changing little v, in the case that v is basically we have periodic technological innovation, but it is kind of slowing down over time as monopoly forms, and everything else can be left the same actually, and then the model can just be replaced with this model. And it turns out, I'm not going to do the math, but it turns out that k is accelerating whenever p is less than 1. In other words, and this is really the big thing. I might prove this in like a nerdy follow-up video for those that are interested. You have to kind of like actually evaluate an infinite product, so that's not good viewing for regular people. But you can show that when you're modeling it this way, you get an accelerating composition of capital, and by virtue of that, an eventually growing reserve army whenever p is less than 1. So for example. So that's pretty interesting, but because what that means is that, like up here, this works. This gives you a growing reserve army. Because it gives you an accelerating K. This does not. And this also does not. In fact, this one is kind of special because this is kind of a like border point. This is kind of where the composition of capital is actually just like a straight line. So with all that said, I think we're finally ready to jump into the next Desmos model. So if you click the, I think it should be the second link in the description, you should see a link to a Desmos model titled Reserve Army under Declining Dynamism, I think is what it should be called. It is. So go ahead and click that. So when you click it initially, all you should see is this boring picture in front of you. And what you see is just a picture of the function, r of t. This is the dynamism as a function of time. So you start out with 0.95, as you can see. You can change it. We had ours set to 0.95, so this would be at 20 here. But you can change it to whatever you want. And basically by changing it to whatever you want, you're changing, what the initial, how strong the technological change is in society initially. So with 0.608, it starts out at 0.608, but no matter what you started at, it gradually, slowly approaches 1 over time. Or, slowly, it really depends on p. So, then down here, you can change p, and you can change from that, like, how fast it's going to approach 1. So if I make p big, p is basically, right now p is 0.5, so this is basically a square root. But as you make p bigger, you're going to get kind of a faster approach towards 1. As you can see, I'm kind of approaching 1 at a speedier rate than I was before, right? And as I get past 1, then I get a pretty dramatic approach to 1. So how fast you're approaching 1 depends on p. I'm going to go ahead and start it out at 0.5 so you can see some stuff. So 0.5 is a pretty slow approach towards 1, but I think it also could be reasonable as a null hypothesis for what reality is. But let's go ahead and turn these things on one at a time. You have to be really careful with this app because Desmos really hates these products. So if you turn on everything at once, you're gonna get some real slowdown. But let's start with K. So here's the composition of capital. Let me change the axes a little bit. So I'm gonna go make this kind of not that big, maybe 20, and then I'll make this go to like 50. So here's the composition of capital, and with p equal to 0.5, you still get an accelerating composition of capital. So you have a declining rate of technological change, but you nonetheless have an accelerating rate of rate in the composition of capital, and you can see how changing the rate at which the dynamism slows down affects the composition of capital. As I move towards 1, you can see that I'm getting a slower and I'm at all points having a growing composition of capital, but I just have a slower and slower growing one. And then finally, when I get to p equals 1, you can see I have a continually increasing composition of capital, but it's a straight line. It's a constant slope. The slope isn't increasing or decreasing. But then when I exceed 1, when I get to the really fast growing, approaches to 1, then at that point I still have an increasing composition of capital, and it still is unbounded. It's going to get as big as it wants. It's basically like a logarithm at that point. These curves that you have for the composition of capital once you get past 1 are basically polylogarithmic. Actually, it might not be polylogarithmic. This might actually be more like a square root function. I'm actually completely unsure whether or not it's like the square root function or like some kind of logarithm. Either way, it's unbounded, and I don't care enough to figure that out. And so in all cases, the composition of capital is increasing over time. And so in all cases, the rate of profit is falling. But only in about half of these cases is the reserve army going to actually be growing. So let me run through a few of these cases, and I'm not going to actually just do all of this live. I'm going to set these graphs up before filming because they take a long time to load, because Desmos really, really hates these products. And for you too, if you're messing around with this app and you change some setting, you might have to wait a few minutes to see the things that are loading. If you want it to go a little faster, I recommend keeping this thing, y of t, just off entirely, and this to only turn on if you really want to see the total number of workers as a function of time. Obviously, that's pretty important, and so we have that displayed here. So basically, what I have here is a situation in which we start at the exact same technological dynamism as in the previous model, 0.97. And so I said that when you're less than 1, you still have a growing reserve army eventually, and you can see that here. The shape of the graph is a little different now than it used to be, right? It's a little kind of more, I don't know what to call it, but nonetheless, you can see that it does hit a peak and then it falls again. And we have a falling rate of profit. So this black curve is the rate of profit, and it starts at like 0.24, and then it kind of drops over time. By the time the reserve army starts to inflate, it's at just 0.047. And then the demand for labor, you can see it starts at 0.079, so about 7% or 8% per period, and then it eventually goes negative, just as before. And this is all despite a slowdown in the rate of technological change over time. So this is an important case, I think, to note, because what we have here is a slowdown in the technological growth over time, either due to diminishing returns in science or due to centralization over time, and nonetheless, we still have a growing reserve army, because the slowdown over time of the technological change is not dramatic enough to counter any of the things we said already. Here I've just turned one more function on. I turned on the composition of capital over time, and you can see that the reason that you get a falling rate of profit is because the composition of capital is increasing, and the reason that you get a growing reserve army is because the composition of capital is accelerating. You do have some curviness here in the upward movement. So that's why P equals 0.7 gives you a growing reserve army. It's because not just is the composition of capital increasing, it is also accelerating, which you can clearly see from the picture here. So here I've changed the graph now. I've changed the setting of P from 0.7 to 1. And so now we're on our border case. And the reason that this is a border case is that at a rate of decline into technological dynamism of this sort, you get a composition of capital that is not accelerating and also not decelerating. It's just a straight line, but it is nonetheless increasing. It's not accelerating with respect to time. The acceleration is 0 here, but nonetheless, the composition of capital is increasing, and because of that, you have a falling rate of profit. Right, the profit rate is falling, and it's not even falling particularly slower than before. And you have a falling demand for labor over time. If I look at this green graph, you can see I start at 0.8. And I fall towards 0. I get pretty close to 0 by like the 80th period, but it's never going to actually go negative. It's going to stay positive forever. And so the third and final case I'm going to show of this model is the case when P is equal to 1.4. And that's a strong enough rate of decay in the technological change over time that what I get is a composition of capital that is, again, continually increasing. And this will go to infinity. This is a logarithmic curve. But nonetheless, it is decelerating. It is constantly increasing, but at a slower and slower rate rather than a faster and faster rate. And so because of that, I pretty much just get more of the same. I get a rate of profit that is falling. Nonetheless, it's still falling because the rate of profit is still increasing. It's going to fall slower. You can see it actually, it takes a long time to fall, but it's still going to be falling, and it's eventually going to hit 0. And you have a continually declining demand for labor. And this also will eventually hit 0 because this will always hit 0 if the rate of profit is going to hit 0, because again the demand for labor is bounded below the rate of profit when you have increasing technological dynamism over time, or just positive technological dynamism over time. And so so this is kind of just more of the same. You get an increasing workforce over time that increases at a slower and slower rate. So it's all the same dynamics, except that K is now decelerating rather than accelerating. So there you have it. There's like a second model in which you have kind of a less of a dramatic assumption about how technological change works in society. I think this model is pretty cool because it shows that this tendency within capitalism for an eventually growing reserve army is actually quite powerful. It's pretty resilient to counteracting factors. The main counteracting factor being slowdown, just general slowdown. It can still happen despite the general slowdown, and I think that's kind of worth noting. But aside from that, there's not much more to say using this model because we've said a lot of this stuff already. Maybe just to kind of reiterate a little bit about like the assumptions for this model is that this model uses a falling rate of profit argument in order to kind of get that the rate of accumulation is shrinking, But the rate of accumulation is always kind of related to the rate of profit. And this argument works to the extent that the rate of profit is falling for any reason. It doesn't have to be the technological changes that give you a shrinking rate of accumulation. In fact, it doesn't even have to be a falling rate of profit that gives you a falling rate of accumulation. Remember, the rate of accumulation isn't just the rate of profit, it's the rate of profit times the rate of reinvestment. So if monopoly forms and that leads to the capitalists not really caring enough to reinvest much of their surplus into the accumulation of capital, then you could get this effect without even having a falling rate of profit. So that's maybe worth noting as well. In fact, if it's really A that's shrinking and not the rate of profit, then I think it's actually the case that you can get a negative demand for labor without even having an accelerating composition of capital, because you're reducing the bound that the change in the composition of capital has to exceed. And so it's actually possible, if that'd be a cool thing to add to this model, actually, is a changing A. Because I think at that point you could definitely get an eventually growing reserve army without an accelerating composition of capital. And when you think about the situation in which you do get a declining A, it's pretty much this situation in which you have monopoly forming. So if you have monopoly forming, then yeah, you're going to get a slowdown in the overall technological changes, but you're also going to get a shrinking of A because the capitalists won't care as much about reinvesting in order to compete with each other. And so it's actually probably the case at that point that you might even have a stronger case for the eventually growing reserve army with monopoly than you do without monopoly. I just thought of that. I'm not changing the model because I'm sick of this project, but that'd be kind of a cool next step for one of these demonstrations. But in any case, I think that kind of does it for this model. Not a whole lot to say compared to the other one, since we already said a lot of the stuff. And it also kind of does it for, I think, the evaluation of the technological argument for a growing reserve army. But we're actually in a position to pretty easily add a whole nother dimension to the argument for an eventually growing reserve army. Since we finished the argument that Marx was trying to give in Volume 2, we can actually bring in circulation, and if you bring that in, if you bring in the disproportionality model from the reproduction schema videos, we can actually find a totally other reason, a totally separate reason why you're going to get a growing reserve army over time. That it's very likely that you can get a growing reserve army over time. So we're going to do that next, but I'm going to split the video here because the thought of having someone sit through all 2.5 hours of this modeling in one sitting just seems, I don't know. I don't want to encourage people to do that. I think it's worth taking a break at this point, letting your brain kind of settle down. And there's another 45 minutes of modeling, more or less. So I hope you'll continue with me to that next video, especially if for nothing else, to hear the conclusions at the end before we transition to the overall conclusions to this whole series. But yeah, I hope you'll continue with me to that one because it's pretty cool.